welcome back to another video on my channel. Today we will be talking about friction, but not everything about friction since it's a very expansive concept. But that will be explained when we move on to the actual video, as this is the intro. So let's move on to the video. Today we will be talking about friction and its more practical applications. So instead of deriving formulas or talking about friction very conceptually, I will give an overview of what you need to do and we will solve some problems with it. This is like basically the way of friction that you will need to know if you need to solve problems or succeed in that way. If when you're doing derivations and other stuff, it is more useful in other fields and other concepts. But for now, let's get a quick overview of friction so we can move on to our problems. So, to begin, what is friction? Well, let's say we draw a floor and an object. If this object is moving on the floor, friction is going to be a force that opposes this. Now, this friction is dependent on many things. One, being the normal force, which is perpendicular to the surface, and I talked about a few videos ago. And if you haven't seen the rest of my mechanics series, be sure to go watch that. And the other thing that you will need to know is that this friction is also dependent on something called mu, or the coefficient of friction. This coefficient is only dependent on the surfaces and materials of the floor and the object, not on anything else. So that's pretty much about it for what we're going to use friction today. Now, just a quick preview of what's going to happen in the next video. You will learn about contact force, where if I am moving an object this way, this is going to be my contact force, where I have a vertical and horizontal component, and I even have an angle with this vertical normal force that we will talk about in more detail in the next part of the video. But for now, let's talk about something different and something a little more practical, which is static friction and kinetic. So static friction, let's start with that. So static friction is the object is not moving. So basically what we're trying to do is we're saying, okay, I'm putting a force on this object in this direction, but static friction is opposing that force, and the force is in equilibrium, so there is no movement. Now, the thing with static friction is it is a variable force. So what do I mean by this? I mean that this can take on as many values as it wants up to a certain maximum. Now, what is this maximum? Well, the friction, which is written with this sort of lowercase f, over here I'll draw it in green, and then friction of static, maximum is equal to the coefficient of static friction, which is again dependent on the surface, and multiplied by the normal force. Now, the derivation for this formula will be in the next video, which is going to be friction part 2. Now, the friction, just the static friction in general, doesn't have to be that. It can be less than or equal to the coefficient of static friction times the normal force. So that's static friction. Now, what about the other type of friction, which is kinetic friction? So kinetic friction is a little different in the way that the object is moving in this scenario. It has overcome the force of static friction. But the fourth thing with kinetic friction is it's a constant force. It's not dependent. It doesn't have any variable change. It can't take on multiple values. if you know the coefficient of kinetic friction and if you know all the variables involved, you can predict it completely with accuracy. But with the static friction, it could take on multiple values depending on how much force we put onto it. But the thing with kinetic friction is it's less than static friction. Because, let's say, we just overcame the force of static friction. And if kinetic friction was more than static friction, that means that we would have to overcome another force to get it to move. Again, because we haven't overcome that force. But that's what static friction is. So it leads to a contradiction, and that's not allowed. But what is kinetic friction? Well, kinetic friction is basically equal to the coefficient of kinetic friction multiplied by the normal force. Now, if you were paying attention, you would have noticed that there's different coefficients, which is the coefficient of static friction and the coefficient of kinetic friction. Well, again, these are constants that entirely depend on the surfaces, and they are not the same. Okay, this also, since it's less than static friction and the coefficient of kinetic friction is less than the coefficient of static friction by very simple algebra, that makes sense why if we start to get an object moving, a heavy object moving, it often feels easier to get it moving than, to make it continue moving, than actually having it not move. So that's basically about it for kinetic and static friction and its relation to normal force, which was covered in my inclined planes video and my forces video about what normal force is. So that's about it for our overview of the practical applications of kinetic and static friction, or just friction in general. So let's move on to 2 examples that demonstrate it. Over here, we have our first example. Example 1. There is an object on the floor. It weighs 10 kilograms and a force of 20 newtons is being applied to it. The coefficient of static friction between the floor and the block is 0.3. Find the static friction force. So, first, let's draw a quick diagram of all the forces. So, we have the weight of the object, or mg. Then we have upwards, we have the normal force. Then we have our applied force, F. And then our frictional force, or static frictional force, towards the left. Now, since this object is not floating or sinking into the ground, the normal force is equal to the weight. And if we're assuming g is equal to 10 meters per second squared, where either way it doesn't make a difference to this problem, but we're going to, for this problem, assume g is equal to 10 meters per second squared, then the normal force will be 10 times 10, or 100. Now, if you remember, the static friction is equal to the coefficient of static friction times the normal force. So this is 0.3 times 10, which is equal to 30 newtons. But then why did I give you the force of 20 newtons? It's because I kind of lied to you in this. If you remember from earlier, this is only the maximum static friction that's equal to this. But if we want to find the actual static friction, as I said earlier, it's a variable force. And since 20 newtons is less than 30 newtons, the static friction will adapt. There will be no movement, so the force of static friction will be 20 newtons. And that is the answer to our problem. Now, in this problem, the reason I chose to do this problem is it's not just plugging in algebra, it's realizing that this is a variable force and this is not a constant force, and that's what separates it from kinetic friction. So, that's that, and let's move on to our next example. Over here, we have our second example. Example 2. A block is on an inclined plane with an angle of 45 degrees. The block is moving down the plane with an acceleration of the square root of 2 meters per second squared. Find the coefficient of kinetic friction. So, over here, what we have is we have first an inclined plane. So, let's draw that. Over here we have this, and this. I know that's not really 45 degrees, but let's roll with it. So over here, 45 degrees, we have a block over here. So first, let's model all of the forces. Now, since mg cosine theta is this way, the normal force will be equal to mg cosine of theta, since it's perpendicular to the surface. Now, there are two forces acting in the direction parallel to the plane. We have, first, mg sine theta, which is what's making this to go downwards, and the force of kinetic friction. So, what we want to find is we want to find the coefficient of the kinetic friction. So, let's take all the net forces. First, we figured out that the normal force is mg cosine theta by taking net forces. And since we know that this block is moving down the plane, then we can say that the net force, or our mass, times our acceleration, which is going to be the one given in the problem over here, this is going to be equal to, first, mg sine theta minus the micro k, or our coefficient of kinetic friction, times mg cosine theta. So, now again, we'll assume g to be 10 meters per second squared for the purposes of this problem. So, what we're going to do is we are going to isolate everything. First, we can factor out m and divide it out of the equation, so that's not necessary. Then, what we can do is we can plug in our angle value of sine and cosine, and I think that's going to help us a lot. So g times the square root of 2 by 2 minus micro k times g times the square root of 2 by 2, since sine and cosine of 45 are the same. Now, factoring out g squared of 2 by 2, we get a is equal to g squared of 2 by 2, 1 minus micro k. So, now we know what our full equation is. Now, let's plug in our values for a and g and isolate the 1 minus micro k. So, we have 1 minus micro k is equal to, now this acceleration times the square root of 2 over g. Now, since g is equal to 10, and acceleration is equal to the square root of 2, so the square root of 2 times 2 is 2, so we get 1 minus micro k is equal to 2 over 10. Now, if we bring micro k and isolate it, we get micro k is equal to 8 over 10, or the coefficient of kinetic friction is equal to 0.8. So, that is our final answer and the solution to this problem. So, that's really about it for this video. Thank you so much for watching, and if you enjoyed this video, please make sure to like, subscribe, and hit that notification button for more awesome videos just like this. And if you really want to, make sure to comment down below to give any suggestions or anything, as it'll really help me improve the channel for all of you. So, thank you so much for watching once again. See you in the next one, and bye-bye.